Now let's go with some applications. 7.3 of our textbook, section 3 of this notebook. Usually, the application part is the most important part of any chapter, especially in statistics class, but I would regard this chapter as one of those rare exceptions. The reason is because what we can do as an application is a little bit limited here. Here are 3 example problems I selected, and the first problem will make a lot of sense because you have done this one before. The second is equally as straightforward, but both of them have a little bit of defect or some questionable aspects built into it, to tell the truth. Okay, let's begin. The intelligence quotient scores are normally distributed with a mean of mu equals around 100 and the standard deviation of sigma equals about 16. If one person is selected at random, what is the probability that the selected person's IQ is between 90 and 105? This is the very same problem we did in chapter 6. Maybe not the exact same numbers here, but very same type. Mu 100, sigma 16, even those were the same. So let's talk about it very quickly. We have this kind of picture where we have to find out the area of the shaded region between 90 and 105. Well, we have normal distribution around x equals 100, and then 90 is over here, 105 is over there, and we want to find out the probability of the middle part, which means the area of the strip. That corresponds to the area of this green strip in the standard normal, where we have to find out the z-score, z1, and that z-score over here, z2. How do we find those z1 and z2? Well, we have this old friend, x minus mu over sigma, x minus mu over sigma. Just put those in and do the computation. And then you get negative 0.625 and 0.313 approximately speaking. And look up the z-table, negative 0.63 approximately speaking, and then you're going to get a figure that is pretty close to this from the normal table. This one is a little bit more accurate because I use Mathematica to calculate a little bit better, but I will accept any figure you get from your normal table because, after all, the preferred method from our textbook's author is coming from the normal table, so I will allow any kind of error that is coming from the normal table. Same with this second probability coming from the second z-score. If you look up the normal table, you're going to get something pretty close to it. This one is a little bit more accurate. By the way, these figures are related to these probabilities. Shaded to the left-hand side, as always. Shaded to the left-hand side, as always. Subtracting one from the other, we get the middle part, which is the strip that we wanted to find to begin with. And that's the probability, 0.356 something. In other words, if you select one person at random, what is the probability that he or she will be in between 90 and 105 in terms of IQ? Well, according to this, it is about 0.35 something. Now let's answer the second question. What if you have a sample of 10 people and then track down the mean of that? Well, we have similar kind of picture, but it'll turn out these pictures are not exactly right. I pictured like these rather intentionally, and later on we're gonna get a little bit more surprising result a bit later. Maybe not. Good students will not be surprised at all. After all, we have different denominators, so we have different z-score. Okay, let's find out the z-score. x1 minus mu over not just sigma but standard error, which is sigma over square root of n. you have to divide by not just 16 but 16 over square root of 10. Calculate, you get negative 1.98 approximately speaking. Look up appropriate figure from the z table. You're gonna get a figure pretty close to this. Do the same thing for second x value, 105 minus 100 over the standard error, 16 over square root of 10. Punch your calculator in and you get appropriate z-score. Look up the z-score from your z table. You get appropriate probability, something similar to this. This one and that one are coming from Mathematicas computations, so they're a little bit more accurate than what you get from your z tables. And they correspond to the left hand side. Okay. This shaded area, that shaded area, this shaded area, that shaded area. Subtracting one from the other, you get .81 something, which means the probability that the mean value of the random sample of 10 people is 0.81 something, significantly higher than the probability that one individual falls into that range. That's what this mean is doing. If you take the average of really large sample, then your confidence level goes up and up and up. If you use a sample, if you use a random sample of 100 people, then the probability calculated as such will become even bigger. Next example is pretty similar too. The Bureau of Labor Statistics provides compensation information on services for various positions. As of May 2008, the national average salary for RN, registered nurse, was 65,130. Suppose that the standard deviation is 9,385. Find the following for the mean and a random sample of 100 such nurses. Well, the Bureau of Labor Statistics finds all these, and then maybe all the registered nurses have to report their incomes through IRS. So these figures, population mean and the population standard deviation, may be real, but that kind of situation, that kind of circumstance is really rare, to tell the truth. Most of the time, the parameters of the population are difficult to find. The population mean, is something we want to estimate because we don't know precisely. That's why we usually do sample study to begin with. Population standard deviation is even harder to estimate. So this problem is kind of backward. Well, the same thing applies to the previous problem too, to tell the truth. In that sense, these two problems, in terms of application, well, only to a certain degree. Early on in the first video of this chapter, I said we can do only a limited amount of application. Well, that's what I meant. But anyway, let's finish this problem. Okay, we are looking for something like this. When n is 100, that's sample size, and the mean is about 65,130, and the standard deviation is about 9,385. Under that circumstance, under that condition, we have to find out the probability that the sample mean does not reach 63,500. That's what we have to find out. x bar is less than 63,500, so we have to shade the left hand side of 63,500. This is kind of backward. This time x bar exceeds 66,000, so you have to shade right hand side of it. And the third problem is somewhere in between 63,500 and 66,000, in between those two. Let me just show you the pictures, and I'm going to leave the details to students. And here's the picture for the first problem. Yes, the middle here, the expected value is 65,130. This is 63,500. X bar is even less than that, so you have to shade left hand side of it. That corresponds to this shaded part, the red part of the standard normal. And what is the z-score using, well, x minus mu over standard error? That's something you'll have to do. Next problem, you'll have to shade the right hand side of it, kind of like this. But the key is again finding out the z-score. And the third problem is finding out the probability in between. In other words, probability of the shaded blue region or the red region. What do? Well, we get the z-scores, get appropriate probabilities, subtract one from the other. That's basically it. Now we'll have just enough time to do one more example. This time let's go over to a normal approximation of the binomial, but this time let us use proportion. Let us use the average rather than the sum. And okay, here we go. And when one ball is selected, here are the mean and the standard deviation formula, square root of p1 minus p. That turns out to be the standard deviation when you select one ball. When you select n times with replacement, then you have sigma over square root of n. That's the central limit theorem. So dividing by n, inside we have square root of p1 minus p over n. As a matter of fact, we went through this formula in the previous chapter as well, but in the previous chapter, in chapter 6, we only did an example problem regarding the sum. Well, this time we are doing that about the average. Now let's find out the z-score. How do we do that? More than a fourth? Okay, 1/4. So that is my x value. So x minus mu will be 1/4 minus the expected value. There are 2 green balls out of total 10, so 2/10. So we get 1/4 minus 2/10, as you see over here. The denominator will be the standard error, square root of p1 minus p over n, and that's going to be 2/10 times 1 minus of that, 1/10, divided by 50. Calculating everything using your calculator, you're going to get 0.88 something. That computation is not difficult. Once you get the z-score, then finding out appropriate picture and looking up the z-table to find out the probabilities is not going to be too much of a deal. Once you do that and to find out the probability, you're going to get 0.88 something. At least that's what I got from Mathematica's computation. By the way, you can find out the precise probability using the binomial, and comparing these two values, well, 0.186 versus 0.1884, close enough for approximation.